Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on February 4th, 2026, just 3 days ago. It presents a unified view that mathematically connects isolated control methods, such as low-rank adaptation and local fine-tuning, proving they all operate as dynamic weight updates. The paper is titled, Why Steering Works, Toward a Unified View of Language Model Parameter Dynamics. And as we'll see later, this theoretical breakthrough leads to a new way to steer models that preserves their reasoning capabilities much better than current approaches. And for those interested in the implementation, the authors have shared their code on GitHub. So Figure 1 illustrates this unified perspective by breaking down how different methods modify the model's linear layers. On the left, the diagrams display local weight fine-tuning, low-rank adaptation, and vector steering as part of the same family. The authors show that all three act as dynamic updates to weights or biases, driven by a control multiplier, M. Moving to the right, the charts demonstrate the resulting trade-off. As you increase that multiplier to boost preference for a target concept, the utility, meaning the model's general coherence, starts to drop in an inverted U-shape. So, Table 1 formalizes this by mapping each method to a specific component of the affine transformation equation. The top row shows that local weight fine-tuning updates both the weight matrix, W, and the bias vector, B. The middle row illustrates how low-rank adaptation restricts changes to the weights, using parameter-efficient low-rank matrices. Finally, the bottom row reveals that a steering vector is mathematically equivalent to simply updating the bias term. The key insight here is that all three include that scalar multiplier, M, which acts as a volume knob for the intervention. Well, having established the math, Figure 2 confirms that these methods behave remarkably similarly in practice. The top two rows display results for vector steering methods like diff-mean. Here, notice how the solid preference lines rise and flatten, while the dashed utility lines peak near zero and then drop off. The bottom rows reveal the exact same pattern for LoRa and local weight updates. This consistency proves that regardless of the specific intervention, the trade-off between gaining control and losing coherence is universal. Alright, Figure 3 provides the geometric intuition behind this trade-off, introducing the activation manifold hypothesis. On the right, the diagram visualizes the model's valid internal states as a curved surface. Steering works by adding a linear vector, represented by the straight arrow, to push the model toward a concept. However, the top left panel shows that while this increases preference projection, the linear path diverges from the curved surface. The bottom left panel illustrates this as validity decay. As the steering factor increases, the activation drifts off manifold into undefined space, causing the loss of coherence. Okay, to validate that geometric theory, Table 2 presents the curve-fitting performance of the author's mathematical model. The columns show R-squared values for preference and utility across datasets like psychopathy and power seeking. Testing on both Gemma 2 and QN 2.5, the rows cover all intervention types, including weight, LoRa, and vector methods. The results are remarkably strong. The deep blue shading indicates that R-squared consistently exceeds 0.95, often hitting 0.99. This confirms that the validity decay equations accurately capture the real parameter dynamics. So with the theoretical model validated, Table 3 demonstrates how the author's new method, split, performs on actual tasks. The rows are organized by model, covering Gemma 2 and QN 2.5, and by intervention form, including local weight and low-rank adaptation. Across the columns, the table reports accuracy and concept scores for datasets like psychopathy and power seeking. Notice the yellow highlights, which indicate the best results. The split method consistently dominates, particularly in the X-bench harmonic mean, confirming that it steers behavior effectively without sacrificing the model's ability to follow instructions. Well, Figure 5 broadens the scope by examining these dynamics on two safety-critical datasets, power seeking in the top panel and psychopathy in the bottom panel. Across both models, we see the same fundamental behavior, where solid preference lines rise and saturate, while dashed utility lines decay. Interestingly, the authors note that utility doesn't always peak exactly at zero. This slight offset implies that the base model's original state isn't always perfectly aligned with the optimal manifold for valid generation. Wrapping up, two takeaways stand out. Distinct control methods like low-rank adaptation and steering are actually just variations of the same dynamic weight update mechanism. This insight reveals that the trade-off between control and coherence is geometric, Pushing a model too hard drives it off its valid manifold. The resulting split method finally lets us steer behavior without breaking reasoning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.